Everyone knows how a motor rotates. The principle sounds simple. It's just magnets, like poles repelling and opposites attracting. If you ever took apart a Mini 4WD motor as a kid, you definitely saw two black permanent magnets inside. But if you take apart an early Tesla Model S motor, or one of those massive industrial motors in a factory, you'll discover something very counterintuitive. There are absolutely no magnets inside. Seriously, not a single one. The rotor looks like just a hunk of iron and some metal bars. So here's the question: without magnets, once this motor is powered on, what exactly is it attracting? How does it grab that rotor out of the thin air and make it spin like crazy? This is the most fascinating and misunderstood physical magic of the induction motor we're talking about today. To solve this mystery, we first need to look at the motor in two parts: the stationary outer shell, the stator, and the rotating center, the rotor. First, let's look at the shell. It is packed with copper coils. When we pass alternating currents through them, even though the coils themselves don't move, the magnetic field generated by the current starts to move. It's a bit like a stadium wave at a baseball game. The spectators stayed in their seats, but the wave keeps traveling around the stadium. We call this a rotating magnetic field. All right, now there's an invisible magnetic field spinning wildly on the outside. Here's the key. How does that magnetless rotor in the middle react to it? This is the classic Lenz's law in physics, or we can personify it. Imagine it as a very lazy person who hates change. When the external rotating magnetic field sweeps past the metal bars on the rotors, the rotor senses a change in the magnetic field. Metal is interesting. As long as the magnetic field is changing, it gets annoyed and wants to resist that change. To resist it, the metal bars on the rotor automatically induce a powerful current. Listen closely. Here is the crucial part. Once there is a current on the rotor, based on the principle of electromagnetism, this originally non-magnetic rotor is instantly forced to become an electromagnet. So, to answer the opening question, how does it attract without magnets? The answer is, it didn't have magnets to begin with. The external electricity forced it to become one. Now the rotor has become a magnet. It realizes the external magnetic field is moving fast and cutting through it. To stop being cut and to stop feeling that magnetic change, what is the rotor's only option? It has to run with it. It must desperately chase the rotating magnetic field. If it runs as fast as the magnetic field to the rotor, the field would seem stationary and it would no longer be cut. So, the operation of an induction motor isn't actually a simple matter of attraction. It's a race that can never be won. The external field leads, and the rotor chases. And the most brilliant part is, the rotor can never catch up. Why? Because if it did catch up and the speeds matched, there would be no relative motion and no cutting. The current in the rotor would vanish. The magnetism would be lost, power would be cut, and it would slow down. So it must always stay just a little bit slower, maintaining a sort of ambiguous distance. Engineers call this slip. This is the beauty of the induction motor. It doesn't rely on expensive rare earth magnets. It only needs copper and iron. It uses physical induction to transmit energy wirelessly. See, even though it has no magnets in its belly, it uses the laws of physics to create its own powerful magnetic force.